In the last video, we learned a little bit about what the expected value of a random variable is. And we saw that it was really just the population mean, the same thing. But with a random variable, since the population is infinite, you can't take up all of the terms and then average them out. What you have to do is say, okay, each of these terms occur with some frequency or with some probability, and you kind of just take a probability-weighted sum, which we saw in the last video was the exact same thing as adding everything together and dividing by the number of numbers, except that that method worked with an infinite population with a random variable is, because you can just keep on performing the experiment that generates the random variable. And then we actually calculated the expected value for the particular binomial distributions that we studied, especially the one with the flipping of the coin. In this video, we'll find a general formula for the mean, or actually for the expected value of a binomial distribution. So if we say that the random variable x is equal to the number of, I don't know, we could call it successes, the number of successes with probability p after n trials. So I'm being a little bit general here. I mean, I could have said, the number of, successful heads which have a probability of 0.5 after 10 flips. That's the same thing as this. I'm just being a little bit more general here. And now we'll actually figure out what the expected value of this is. As we saw, if you actually figured out the probability distribution for this random variable, you get that nice binomial distribution that looks a little bit like a bell curve, and we'll study more about bell curves later. And before I actually show it to you, I'll give you the answer, because the answer to some degree is actually pretty intuitive. The expected value of this random variable is n times p. Or sometimes people will write p times n. And let me make that a little bit more tangible for you. So if I said that x is, let me do it in a different color. Let's see, x is equal to the number of baskets I make, where I'm talking about basketball, not basket weaving. Number of baskets I make after 10 shots, where I have, the probability of me making any one shot is, 40%. We know that the expected number of baskets I make after 10 shots, right? So we know that the expected number of baskets I make after 10 shots, where each of my shots is 40%, all I have to do is multiply the probability times the number of baskets I'm taking. So I multiply probability times the number of baskets, or the number of shots I'm taking, which would be equal to 4. So I know I said, and you really shouldn't necessarily strictly view expected value as the number of shots you should expect to make, because sometimes probability distributions can be kind of weird. But in the binomial distribution, you can kind of view it that way, that this is the number of shots you would expect to make, or you can kind of view it as the most likely outcome, that if you have a 40% shot percentage and you take 10 shots, the most likely outcome is that you'll make 4 shots. You still might make 6 shots or 3 shots, but this is going to be the most likely outcome. And in my head, the way I think about it, the way it makes intuitive sense is that every time you shoot, you have a 40% chance of making the shot, right? So you could say that you always make 40% of a shot. And if you take 10 shots, you're going to make 4 whole shots. So that's one way to think about it, and why this might make a little intuitive sense. But now let's prove it to ourselves that this is really true for any a random variable that's described by a binomial distribution. So in a binomial distribution, what is the probability? So if I say, what is the probability that x is equal to k? And I know it just gets a little complicated sometimes, but I'm just saying, what's the probability? Let's say in this basketball analogy, it would be, what's the probability that I make k could be 3 shots or something like that. So that's what we're talking about, and that we learned was, if we're taking n shots, we're going to choose k of them. Right? We did that several times in the last couple of videos. And then we multiply that times the probability of any one of those particular occurrences. So if I'm making k shots, it'll be the probability of me making any one shot, which is p, to the kth power, right? P times itself, k times. That's the probability of me making k shots. And then the rest of the shots I have to miss. So the probability of a miss is 1 minus p. And then how many shots? If I've made k shots, the rest of the shots I have to miss. So I'm going to miss n minus k shots. So in any binomial distribution, this is the probability that you get k successes, right? And we know that the expected value, the way you calculate an expected value of a random variable is you just take the probability weighted sum. And I don't want to confuse you too much. And you know, if your main takeaway from this video is just this, that's good enough. You should feel good. Now it'll get a little technical, but it'll hopefully make you a little bit more comfortable with sigma and sum notation as well, and it'll make you a little bit more comfortable with binomial coefficients and things like that. But just going back, the expected value is a probability weighted sum of each of these. So what you want to do is you want to take the probability that x is equal to k times k, and then add that up for each of the possible k's. So how would I write that? So the expected value of x, the expected value of our random variable that's being described as a binomial distribution, it's equal to the sum. And we're going to sum all of the values that k can take on, right? So k can start at 0. That's in the basketball version. I make no shots, all the way to n, which means I make n shots. And for each of them, you want to multiply k. So the outcome, so I made k shots, times the probability that I make k shots. Well, what was the probability that I make k shots? That was this right here. So it'd be k times n, choose k, times p to the k, times 1 minus p to the n minus k. And now we're just going to do some algebra, some sigma algebra, I guess you could call it. So the first simplification we can make is we're summing from k equals 0 to n. So the first term here is going to have a k equals 0 here. This is going to be 0 in the first term. So if this first term is 0, then this whole thing is going to be 0, and the k equals 0th term won't contribute to the sum, because this whole thing will be 0. So we can, let me write that out, because I think it's a, so this sum could be written as 0 times n, choose 0, times p to the 0, times 1 minus p to the n minus 0, plus 1 times n, choose 1, times p to the 1, times 1 minus p to the n minus 1. And then you keep adding all the way you get to, until you get to k is equal to n. So it'd be n times n, choose n, times p to the n, times 1 minus p, n minus n. Right? This is just another way of writing this sum up here. And what I just said is the first term, which is this term, is going to be equal to 0, because k is equal to 0. 0 times anything is 0. So we can ignore that term, and we can rewrite this sum as essentially this sum right here. This sum right there. And so if we were to do that, we essentially just rewrite this thing up here. So the expected value of our random variable is equal to the sum. And we don't have to go from k equals 0. We could start at k equal 1 now. From k equals 1 to n of the same thing, k times n, choose k, times p to the k, times 1 minus p, n minus k. And let's see what we can do from here. All we did so far is we got rid of that first term, because that's kind of the trick we'll use to simplify this eventually to the result that we want to have. So let's write out the binomial coefficient and see if we can do something there. Oh, look at this. My iPod wants to sync. Let me get rid of that. All right. So then, where was I? Okay, so then this is equal to, I'm just going to write out the binomial coefficient, k equals 1 to n. K times, this right here is n factorial over k factorial over n minus k factorial times p to the k times 1 minus p to the n minus k. And here we can make a little bit of a simplification, because what's k divided by k factorial? Maybe I could rewrite it a different way. K factorial is k times k minus 1 times k minus 2, and so forth, all the way until you get to 1, right? This is k factorial. So k factorial could be written as k times k minus 1 factorial. Right? It's k times, and then the number 1 smaller than k times all of the numbers below it. Right? So let me rewrite. So this could be rewritten as k times k minus 1 factorial. And the whole reason why I did that is so I can cancel this k out with that k. So if I cancel that out, I think this warrants rewriting the whole thing again. So now we have, I guess you could argue, simplified it to, it equals the sum from k is equal to 1 to n of n factorial over k minus 1 factorial times n minus k factorial times p to the k times 1 minus p to the n minus k. And let's do another simplification. Now, what I want to do, and we kind of know where we're heading, right? We want to just, this should simplify to n times p. So let's see if we can factor out an n times p, and then let's see if we can turn everything else into a 1, and then we would be done. So we could rewrite n factorial using the same trick up here. N factorial can be rewritten as n times n minus 1 factorial, right? By the same logic. And then p to the k could be rewritten as p times p to the k minus 1, right? And then we can factor out this n and this p, and we'll get this is equal to np times the sum from k is equal to 1 to n of, let's see, we factored that n and p out, n minus 1 factorial over k minus 1 factorial times n minus k factorial times p to the k minus 1, that's not in the denominator, this is just a regular, times 1 minus p to the n minus k. And we're close. Remember, we want the result that the expected value of our variable, and that's what we were doing before, that this should be equal to this. So we'll be done if we can just show that this whole thing here equals 1. And to do that, I'll make a simplifying substitution. Let me make the substitution, I don't know, let's say that a is equal to k minus 1, and that b is equal to n minus 1. And then what would n minus k equal to? Let's see, if a is equal to k minus 1, then a plus 1 is equal to k. And then here, b plus 1 is equal to n. So then n minus k would be equal to this, a plus 1 minus this, minus b minus 1, which is equal to, these would cancel out, which would equal a minus b. And let's see if we can simplify this. So this whole sum will then turn into np times the sum from, okay, when k is equal to 1, that's the same thing. When k is equal to 1, what is a is equal to? A is equal to 0. From a equal to 0 to, now when k is equal to n, what will a be equal to? If this is equal to n, if k is n, then a is equal to n minus 1, right? So you could have a equal to 0 to a equals n minus 1. But n minus 1 is the same thing as b, right? So we could rewrite the sum there. And that's always a little confusing. You might want to pause and think about that a little bit. But I realize I'm already over time, so I'll just keep moving forward. And then we had b is equal to n minus 1, so that'll be b factorial over k minus 1, we made the definition that that's equal to a, so that's a factorial. And then over here, n minus k should be a, oh, you know what, I reverse this. N minus k should be b minus a. N minus k, right, it should be, n is b plus 1, so it's b plus 1 minus a plus 1, minus a minus 1. Right, so the 1's cancel out and you get b minus a. So the n minus k will become b minus a factorial. And then p to the k minus 1. K minus 1 is p to the a. And then times 1 minus p to the n minus k. We already showed that n minus k is the same thing as b minus a. And then here, and we're pretty much done now, this right here, what is this? This is the probability of, well, let me rewrite it a simpler way. This is equal to np times the sum from a is equal to 0 to b. What is this? This is b choose a. If I have b things and I want to choose a things from them, how many different ways can I? Times p to the a times 1 minus p to the b minus a. What is this thing here? This is you're taking every term of the binomial distribution. So you're saying, what is the probability when a is equal to 0? This is the probability for each of the a's, right? And you're summing up over all of the a's you can achieve. So if I were to draw a quick dirty distribution like this, and if a is equal to 0, you have a certain probability, then a certain probability for a equals 1, and then another probability and it goes higher, and then it's it's a bit of it's like a bell curve, something like that. This term right here is each of these, right? Each of these boxes, you could say, represents one of these terms, right? When a equals 0, it's this term. When a equals 1, it's this term. When a equals 2, it's this term, all the way to b terms. But we're summing them up. So we're summing all the probabilities, right? We're summing over all of the values that our random variable can take. So if we sum up all the probabilities that a random variable can take, or so we're summing over all the values, this is going to sum up to 1, right? If this is like saying that this is the probability of heads plus the probability of tails, or you could say in the flipping of a coin analogy, this is the probability that I have 1 heads plus the probability I have 2 heads plus the probability I have 3 heads plus the probability I have 4 heads, all the way to the probability I have b heads. So it's pretty much every circumstance that can occur. So this is the sum over the entire probability distribution, and so that is going to be equal to 1. And so we're left with the expected value of our random variable x is equal to n times p, where n is the number of trials and p is the probability of success on each trial. And this is true only for binomial distributions. This isn't true for any random variable x. It's only true for a random variable x whose probability distribution is the binomial distribution. Anyway, I'm all out of time. I'll see you in the next video.